Alright, this is NCCER Instrumentation 4, Module 3. So this chapter is going to be on tuning loops. The biggest thing one of the biggest things I want you guys to just recognize from this is that tuning and calibration are not the same thing. You have to start with everything calibrated before tuning. Tuning is making the loop function the way you want it to. Like if you had to get, like I always say, if you have a big 100-gallon tank and you want to get that tank up to 50 gallons, how fast can we get it there, or how fast can we control it to get there without going above our means of our pieces of equipment, right? Like I've talked about how you can go too fast and you're missing your set point and stuff like that. So you tune in order to get like a steady curve in order to find stability. The goal of tuning is to find stability. Trade terms, you've probably seen some of these. Bump test is a good one to know. Method of testing the response of a control system by suddenly changing a controller, just to make sure that some like a system is working. Like you might introduce like some sort of movement or something like that, so you know that loop will control back to the set point. We'll talk about integral. They should have. Do they have proportional on there? They have integral and derivative, but not proportional. But like B, the trainer that you're on, and Brandon, the one you did last semester, like you messing with the PID controller. PID is proportional, integral, and derivative. And I just want you to think of that as like increasing levels of control. Proportional is kind of the basic way. Like I have a set point, I need to get there, this is how far off I am from my set point, and it changes based on how far away you are. And then integral and derivative are adding forms of automation to make stuff run a little bit tighter. And you don't always need all three, like you don't always need all three to function, because if you had, say you had like these big tanks out of PBS or any refinery, the big giant tanks that everybody drives past, those things are not going to have to be dead on, like within a half inch of level or something like that. It doesn't matter. So proportional control for something like that would be fine. But if you had, say you were in like a nuclear power plant, a little bit more important to be dead on accurate with some types of controls with whatever they're doing. Lag wouldn't be bad to know. We'll talk about oscillations. Stability, like I said, is going to be most important. The time constant up in the top right, I have highlighted as an online test question. So a measurement of time that describes the response behavior of a particular control system. A single time constant is the time required for a controlled variable to change by 63.2% of the amount that it must be changed to reach steady state. So what that's saying is, I have a tank, 100-gallon tank. My set point is 50. I want to get, my goal is a nice smooth curve to get up to 50 that might move something like this. My time constant is to get to steady state. I'm just guessing, but like from here to here is the 63.2%. So that is your time constant. It's called your PV, not R. It's called your PV time constant. Ed talked about it yesterday. Just the time constant of getting towards your set point. 111 factors that influence loop stability. Second sentence of 111 is highlighted. An increase in response speed usually decreases the system's stability. So like I've said over and over again, like if this was like your normal curve to get to steady state, nice and smooth, if I increase my speed, usually that's increasing gain. So if you remember from like high school, gain is just your rise over your run, so which is also your slope. So if I increase, like that's one. If I increase like that, or if I increase like this, I'm going to increase my stability. Like I've said, you're going to overshoot and then try to come back and eventually get to there. So increase in response speed is going to decrease your ability to get to that stability more than likely. Like there's like I know in college, like we would do circuits like y'all did, and we would go through and see how much gain. Like y'all did that y'all either will or have done that in the trainer, where you bump it from like 20 to 40 to 60 and stuff like that. But we got it all the way like as fast as we could get it, and then even went a little bit above to where our thing would go nuts and it would never get to a steady state because we were trying to go too fast. Page 2. The last sentence of that first paragraph is highlighted. Last sentence of the first started paragraph is highlighted. An unstable system's oscillations increase in amplitude and usually become uncontrolled and potentially destructive. And that's, again, I know I keep drawing on this, but that's what I'm saying. If you get too fast, it's never, and it'll get bigger and bigger and bigger, and you think about, like, that's not a big deal for that little control valve right there. But whenever, like when I worked at the steel mill, we did something that moved the whole coil back and forth. It's called the edge aligner. So when you wrap those big coils up, like the edges are all nice and straight. That's not it is an easy process, but it also messed up quite a bit. But once it tried to start correcting factor, like it would go back and forth, and these are 40-ton coils, like 80,000 pounds that were moving way too fast. It was like not to a dangerous point, but it could have been if the stuff was cranked up too high. Immediate first sentence on the next paragraph. These undesirable oscillations normally occur at a certain frequency, which is known as critical frequency. So critical frequency, well, let me give you, the immediate next sentence is a separate highlight. At this frequency, there is a 360-degree phase shift around the control loop. So just looking at these, once you get uncontrolled and stuff like that, what it means by 360 degrees, like if you are just constantly having sinusoidal waves like this, I didn't do that right. There we go. So if you constantly had that, and I'm splitting stuff right here, if I took this half and put it right there, it's just a big circle, 360 degrees. So if you have 360 degrees of phase shift, it's bad as far as trying to control it or something. And if you get to critical frequency, there's stuff that can happen, like stuff will remain moving and stuff like that. You ever see the video of the bridges that reach critical frequency? You ever seen that, where they just keep till they destroy themselves? You ever seen that? Give me 2 seconds. Like this was a real bridge. So that thing has reached critical frequency in its movement. No way in hell I'd be standing right there. I shouldn't say that. Only at 35 mile an hour wind is blowing.
but this apparently sets up a rhythmic swing in the wind,
Yeah, it's all down
which
the road.
increases with each swing.
I mean, that's what can happen with critical frequency.
I know, like them little walkways and like.
How the heck are they
stuff.
walking? Like, they're nuts.
Finally, the steam road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
And a dog? Who let a dog? Yeah. Yeah, they, like, stuff like that can cause major damage. Last paragraph in that section, I've got the whole thing highlighted for 2 questions. One question comes out of the first sentence and the other question comes out of the whole paragraph. But during controller tuning, the goal is to adjust the loop's gain so that it is less than 1 at the critical frequency. If this is done correctly, process oscillations will die out as quickly as possible and the controlled variable will remain near the set point. This section explores different ways this goal can be reached. So it's going to go into the different forms of adding more and more control, because you can have just proportional control, you can have proportional integral and derivative. It's gonna add, like, and the more you add, the tighter that control is gonna get. Loop tuning, I've got the whole last sentence before 120 highlighted. Just that, or the whole last paragraph. So the one that says during controller tuning, that whole paragraph's highlighted for a couple different highlights. Loop tuning 121 proportional control review. So this is literally just looking at if a system was, it's easy to stay with this system at set points at 50 gallons, I'm at 25 gallons, my error number is 25 gallons, so they change their gain based on how far off they are. That's proportional control. It's proportional to the error. Second to last paragraph in section 121 on the right hand side, so second to last paragraph before 122, first sentence is highlighted. It is important to note that with proportional controllers, typically necessary to make a small adjustment manually to bring the control variable to the set point on initial startup. And that's, so if you're filling up big 1,000-gallon tanks and stuff like that, like, it's better for those systems if you run in manual. Say you had to get to like 500 gallons out of 1,000. Put that thing in manual. Change your output on your controller to open up your valve, and then once you start to get to 500 gallons, turn it down and then switch over to automatic mode, and then the controller will take over there. It's a lot easier on that controller. Controllers are good at controlling like way less error. If there's a massive amount of error, like, it kind of throws them for a loop, just because it's like 100% error. I'm 100% wrong, so they're slamming valves open and closed, depending on what they're doing. Proportional and integral control. So what integral? I'm gonna draw the same exact thing. 150. This is my set point. If I have proportional and integral control, and I have with just proportional control, I can achieve stability that'll go something like this, and it might end up something. If I continue this line out here, like it's pretty dang close, but like I said, big tanks, half an inch off, doesn't matter. But there's still like a minute amount of error once you try to get to that set point. Integral control takes care, literally, of just that. Like it's a correction factor, not really, but kind of. It just corrects to make you be dead on your set point. The highlight for that is on page 3. The second sentence, all the way at the top right of page 3. As a result, the integral function eliminates any offset that exists between the measured variable and the set point, which can occur with proportional control alone. That's the second sentence at the top left of page 3. As a result, the integral function eliminates any offset that exists between the measured variable and the set point, which can occur with proportional control alone. 1, 2, 3, adding on derivative, proportional, integral, and derivative. Top right of the page, where you see PID all the way in the top right through the end of the paragraph is an online test question. Online test question. PID control is recommended in systems where the load on the process changes often and the controller is expected to compensate automatically due to frequent changes in set point, the amount of energy available, or the mass to be controlled. So when you think of PID control, think of with adding derivative, it's for stuff that's changing a lot. Terms and definitions associated with loop tuning. We talked about bump test. Dead time is a good one to know. Like you don't always want to be. It's kind of like a buffer. You don't always want to be taken off as soon as there's an error and stuff like that. Flipping over to page 4, I've got the second bullet point, first sentence on page 4 highlighted, steady state. The steady state condition is the point at which the control variable is no longer changing significantly but holding steady near the set point. This picture that they have, these are the like proportional integral, this is like an old version of what you guys have been messing with, like that PID controller. I think, pretty sure those are Honeywell brand out there, but this is just a little bit older version of that. This is kind of the equation that I was showing you, like 63.2%. That's your lag time, lag or your time constant. So that's kind of how long it takes to get to steady state. So time constant of 1.5. All in the time constant bullet point, the sentence that splits the columns is highlighted. A full response from the end of the dead time to arrival at steady state requires 5 time constants to pass, 7.5 units in the graph. 125, process type identification. Second paragraph, first sentence is highlighted. A non-integrating process, also known as self-regulating process, is one that responds to a controller output change by moving toward a new process value. Everybody remember what that triangle or the delta stands for? Change. That just means change in. CO is controller output, so that is change in controller output. PV is your process variable. So that's whatever your primary element is sensing in your system. Page 5, right after the caution on page 5, first 2 sentences are highlighted. An integrating process, in contrast, is not self-regulating. Once the controller output changes, the process will begin to react and will keep changing as long as the controller output is in the new position. So you can see, like this right here, like your time constant, time constants in order to reach your new level. Controller output, like this is just the change in controller output. So this just might be turning on and off something, maybe turning on a heater, and then maybe this is measuring, or this is your temperature in a tank or vessel or something like that. So this says turn your heater on. How long does it take for me to get up there? 5 time constants or whatever, whatever it is based on the what you're trying to do. Temperature takes a little bit longer for stuff to react. This was on page 6, 8, and 7. But they show non-integrating process and then integrating process and what the differences are. I'm just going to let y'all do section reviews at home whenever you're going through all this. I'm just going to keep going. Stop me if you have questions and stuff. Stop me, but I'm just going to keep on going through section 2. Good? Trade terms. I have repeats per minute. I wish they wouldn't call that RPM. It is an online test question. Repeats per minute, a measure of how fast a signal is being integrated. We used to have to, y'all ever gotten to the math where you have to do integrals and derivatives and stuff? They made us do that in college to figure out like what the actual number, like you could do integrals and derivatives to find what your gain is and stuff, and like that's literally how that math works and stuff, but it was difficult. It was a lot easier to kind of do trial and error to see. I mean, that's very part of the engineering side to kind of mathematically know what you're supposed to set it to, but it was definitely easier just to kind of change your gain and see what works smoothly, depending on your circuit and stuff. Stiction, I don't have it highlighted, but you should know what it is. Like a lot of these control valves aren't brand new and stuff like that, and they could be in a little bit corrosive environment, and they don't necessarily like a lot of times we want our control valves like the stem to move up and down slowly, but there's seals and there's stuff like the stem can corrode, and sometimes they kind of go like bump like that to open up and close, especially because a lot of them have to deal with air pressure, and air pressure is not necessarily a smooth thing. So that's what stiction is not letting the valve move slowly up and down, or steadily up and down. That's an online test question. Or no, sorry, it's not. Repeats per minute is, stiction is not. But you should know what stiction is. Energy balance equation, 211, second sentence is highlighted. In order for any process system to be stable, this equation must be balanced. And then the equation is balanced as a separate highlight. Energy out equals energy in minus energy lost minus energy stored. So this is, if you think about this is for everything we do, even us as human beings. What's our energy in? Food. We're putting in, like, depending on what food we put in our body, it's going to give us different types of energy, and it might be good stuff, it might be bad stuff, and then if we put a lot of food in our body and we don't use that energy, that's how we get fat, and we're storing, like, that's our stored energy and stuff like that. Same thing like with a car. What's energy in a car? Putting gas in it, stuff like that. Sometimes you might put like higher octane gas, so you're putting better energy into your car, and then you have to take. So that's the energy in, and then the energy lost. Like y'all know what the energy lost in, like the main energy lost in an engine would be, like a gasoline powered engine. I guess that could be true. Yeah, like that is the main energy loss. You are right. So driving is the main energy no, that's not energy loss. So that would be your energy out. That's what your energy out would be. Your energy lost, a big loss in a gasoline engine is heat. Heat is a form of energy, right? Like the sun is our main form of energy, heat. So our engines create a lot of heat, and that's all lost. One of the, I know I told, you might not have been, were you here whenever I said what's the best mechanical device that humans have created? Bicycle. Because the only, like our energy in is our muscles pushing the pedals and stuff like that, and then our energy out is actually the movement. The only energy lost is between the gear and the chain, and where that chain meets the gear, and a little bit of movement in between the gear and the chain. And then if you have like tires that slip or something, slip could be a little bit part of that. But bicycles are like between 98 and 99% efficient, whereas like a gasoline powered engine is between 50 and 60% efficient. They're horrible. But everything works like that. Energy out equals energy in minus energy lost minus energy stored. Flipping over to page 8, they go through and show you how to find the time constant. So time constant equals volume or capacity over flow. I don't have that highlighted. I'll be curious to know whenever y'all take the test, if you see that question, like this is one of those ones like I want to see, and then I'll make it right with the class and stuff like that. I don't have anything in 212. 213, first sentence is highlighted. To find out by what percent a process has changed in a given period, use the complete response equation. I don't have the equation highlighted, but that's just going through and seeing how fast stuff happened, and like there's logarithmic equation to see how fast stuff happened. I don't think that's going to be important to as far as like us looking at it from a maintenance standpoint. 214, a little bit behind. Process gain. Process gain is determined. I have the equation in 214 highlighted. K, which is your process gain, is the change in output over the change in input. Change in output over the change in input, and then I highlighted the K. You need to know that K stands for process gain. You might have a pretty easy equation with that, but or question with that, but just know change in output over the change in input. I forgot, Sam said he was over here this whole week. Do that before I forget.
Houston.
That's what I forgot he said that. They go through a practice problem with that you can read through there. 215, we're on page 9. 215, proportional band. I have the last equation on the page highlighted. PB equals 100% divided by K, which remember our K is our process gain. This is an online test question. I want the question, write this down below. What is the proportional band's mathematical relationship to gain? So the relationship is between proportional band and gain is PB equals 100% divided by the process gain.
Can't repeat the question.
What is the proportional band's mathematical relationship to gain? What is the proportional band's mathematical relationship to gain? Online test question. Did I go with that one? Flipping the page, 216. They'll go through the integral time equation to figure out like what you should plug in for your integral. I did not have anything highlighted in that. But it does have to do, that's where your repeats per minute come into play and stuff like that. Because that's what's sensing the difference between like our set point and our actual process variable for integral. Derivative time, second paragraph, first sentence, and 217 is highlighted. The differentiator provides an output amplitude that is directly related to the change of the input and it is a constant that specifies the function of differentiation. If I'm being honest, a lot of this is difficult stuff, and where like I had to go through and learn a lot of this. We went through this a ton when I was in college, and I used it none. It is good to, like, proportional stuff is good to know because pretty much, like, I want you to know that proportional stuff is setting the gain, like how fast something's going to react. Like that's loop tuning. And then your gain is your slope on how fast you're going to get to your set point. And proportional is controlled by your error signal, which is how far off your process value is from your set point. That's the main thing I want you to get from the PID equation and stuff like that. So that's like the next section, 218, like that equation, PID T Like that equation is what you can go through to find the exact numbers that you need to put in for a certain type of control. For our purposes being in maintenance and stuff like that, we're not creating new machines that are gonna control stuff like this. We're gonna be working on stuff, so it's good for us to have an idea of what stuff is, just in order to work on it. Open loop tuning, 222, 221 procedure overview. I've got the first 4 sentences highlighted, a 221, the end of page 11. First sentence is one highlighted and all of it is a separate highlight. For open loop tuning methods, you will need to obtain the necessary process information from the process reaction curve. To generate this curve, you must introduce a signal disturbance or a bump into the control system. Typically, a supply disturbance works well. A sudden set point change is a good way to provoke this situation. Y'all remember doing open loop tuning on that process trainer? That's where you weren't using the controller. Like if I told you to control to 5 inches, whenever we put that valve like halfway open and like some of the water was flowing through it and you were changing the output to try to stay at 5 inches or whatever it was, that's open loop tuning because there's no connection between the height of the tank and the controller output besides you. Like you are the brains of the operation. If you put a controller in there, that's closed loop tuning. If not, then open loop tuning is where you are physically making the change in order to correct the error. On pages 12 and 13, going into section 222, yes, they just time constant method. Second paragraph, first 2 sentences are highlighted in 222. The first method is shown in figure 9 and is referred to as the time constant method. The information required from this process reaction curve is the time constant, process gain, and dead time. So it is good to know, like whenever I talked about dead time, like dead time is kind of a buffer, like, and it's just like this amount of time is like that, like it's nothing. But for a computer, it's like, all right, you made this change. Is this really, like we're really changing right now? And literally like a blink of an eye, like it determines, yes, we are. So then your variable will start changing. Like, yes, we really need to open up this valve. It's not just like a blip or something like that. So dead times are, think of a dead time as kind of like a buffer or a lead-in time. They go through, I think there's a lot of math they go through in these next couple sections to figure out like your time constant method for proportional integral. That's all I had on page 13, 14, and 15. I don't have any highlights for. They talk about reaction rate method. It's just another method of tuning. With going through the math for reaction rate time, nothing highlighted in 223 either. Going on to 230, closed loop tuning. So remember, closed loop tuning is where you're adding a controller. Something's looking at your output, and then the controller is seeing what the error is and making a correction factor based on that. In closed loop tuning 230 on page 16, I've got the first 4 sentences highlighted in 230. Closed loop tuning accomplishes the same basic goal as open loop. The crucial difference is that the controller is active in the process. Like open loop tuning, closed loop methods require you to introduce a disturbance in the process and note its effect. What is different is that the process must be disturbed more significantly and for a longer period. So in order for closed loop tuning to take off, there has to be some type of disturbance. Like a valve opening up a little bit or something. Something has to happen for the automatic mode of the controller to take off. Ultimate period method. So this is just another way of tuning and closed loop tuning. On page 17, that first, the started paragraph, the sentence, it's a sentence right above where you see figure 13 in italics, is a highlight to determine the ultimate gain or proportional band and the ultimate period. Operate the controller in proportional mode alone. The rest of that paragraph and the first two sentences of the next paragraph are a separate highlight. Figure 13 shows the response of a control system that is that ultimate gain or proportional band. As shown, the controlled variable is oscillating at a constant amplitude and frequency. This is critical frequency. A 360-degree phase shift in the control system. The amplitude of oscillations is constant. So that's, again, this picture right here. You can see like our amplitude on these is staying the same. So we have a 360-degree phase shift. If I start at 0, I go all the way up, and then back to 0 would be 360 degrees of change. That's what they're talking about. Nothing else highlighted on page 17. They do the math of this ultimate period method on page 18. They don't go through any of the math. I can't imagine they start throwing that on the test and stuff. I can't imagine they start doing it. But I don't have any of it highlighted. If you want to go through and figure out the math and the time constants and stuff like that, feel free. If you have questions on it, like I don't mind going through that stuff, but for our purposes in maintenance and stuff like that, like I teach, I don't find a lot of value in it. Nothing highlighted in 2.3.2, either the dampened oscillation methods, that's just where you have less of an amplitude. Visual loop tuning 2.4.0. 2.4.1, incremental changes. First sentence of incremental changes is highlighted. Changes of approximately 40% in gain, derivative time, and integral time almost always lead to significant and visible changes in closed loop response. So yeah, if you change something 40% of your gain, I guess 40% of your gain isn't a ton of it, but I know in that lab you go up by 20s. Like your gain is going up by 20, so it's at least 60 or at least 50% you're going up by, and you'll notice how much faster that's going to open up that valve and try to get to that set point. So it's important that you change your gain incrementally, like not changing it from 1 to 50, change it from like 1 to 5 to 10, like increase it steadily. If you're trying to find like a steady state with these PID controllers. Apparent instability, 2.4.2, the whole first paragraph is highlighted. When attempting to visually tune a loop having an apparent instability, it's necessary to first make sure the cause of the loop oscillations is inherent to the loop you're tuning and it's not being caused by another process. After receiving permission from the unit operator, one way to do this is to place the loop controller for the loop you're tuning in manual mode. If the process tends to stabilize in manual mode, the controller most likely requires tuning. So that's just saying, like a lot of times, first step in troubleshooting is put it in manual mode and see if you can control it, and if you can't, then a component is bad. But if you turn it to manual mode and it stabilizes, the tuning in that controller needs to be adjusted to where it can more smoothly control that process. Your gain might be turned up too much. Page 20, 2.4.3. Sluggish response. First sentence of 2.4.3 is highlighted. Two conditions that usually exist in a loop that is experiencing sluggish response are lack of derivative action and a long integral time relative to the process response time. Page 21, all the way on the right hand side of the page, it's this second paragraph, it's the one with stiction in it. The whole thing is highlighted. An example where visual tuning might be more effective than calculated methods of tuning is a loop where stiction is present in the control valve. Many of the calculator approaches rely on linear response in order to be effective. Stiction usually causes a non-linear effect on the process. So you can see Like this would be, our valve position is not linear, like it's stiction, like it's, like you put a certain amount of pressure in there and it might, like you, if your pressure, like the pressure on our control valve was 3 to 15 PSI, right? Well, maybe that control valve's not gonna move. If I go from 3 PSI to 4 PSI, the valve doesn't move at all. Like it's not enough to overcome that stiction, but if I go to 5, then it jumps to 5. And that's what it's saying. Like it can jump along the way, whereas brand new valves and in clean conditions and stuff like that, it's going to be a more linear process where it's going to, from 0 to 100% open or closed, it's going to gradually go up and down, which is what you want, but not always what you get.